Okay, I suppose we'll hop into some math. I mentioned it kind of last class, but I'm trying to make sure we're done next week so you have some time to ask me questions and whatnot. So I don't have anything to say other than let's just mosey on. So last class, we did a bunch of examples of row reduction. That's basically all we did ultimately was did row reduction and then used row reduction to solve systems of equations. We did several examples of that. So as a reminder, if you want to use this technique to solve a system of equations, you first state this thing, the augmented matrix, which you can just read off from the equation. Then you row reduce it to get that reduced row echelon form. So you got the staircase and all the leading entries have zeros below and above. And then you reinterpret it as a system of equations and make a conclusion. So that's either no solutions, there's exactly one solution because it just, as soon as you reinterpret it, it just tells you the solution. Or you have infinite solutions, in which case you just need to say, okay, these were my leading variables, the ones that corresponded to the far left ones in my matrix. All the other variables I move over, right? And then you're done. So we'll before I give you the quiz, I'm going to do an example of that so that you're refreshed on it, because we're going to start talking about matrix operations, and then your head will be full of that, and then I'll be like, okay, let's do an example so that you're refreshed, so that you can go into the quiz refreshed. So just like everything else, we ask ourselves, we've got these matrices. They're a thing we can play around with. So let's do that. Let's play around with them. Let's see what we can do with them. So how do I want to say this? So this is sort of a remark. We often care specifically about diagonal entries. So what is a diagonal entry? Well, you'll have a square matrix like this. When we say diagonal, we mean what's called the main diagonal, which is go from the top left, go through like that. Those entries are on the diagonal, right? So 1, 5, 9 are the diagonal entries of this matrix. You have sort of like a corresponding anti-diagonal, but it ends up not being very interesting, generally speaking. This is the one that we care about for most things. So we call that the diagonal entries. So in this case, it would be 1, 5, and 9. And I did kind of mention that, the entries in this, we would say, this is Aij. This is row I, column J. Where those are just, corresponding rows and columns that make sense, right? I wouldn't say, A5, 6 in this matrix because there's no row 5 and there's no column 6, right? So just stuff that makes sense, which means these diagonal entries are identified by these numbers being the same thing, right? So diagonals, we would just say it's A, I. So for this matrix, it's A1, 1 is 1, A2, 2 is 5, and A3, 3 is 9. Because they're just the same thing. And I'm drawing attention to this sort of notation because when we define matrix multiplication, we're going to define it two ways. I'm going to write down the formula because that's useful for algorithms, right? If you're doing some sort of loop over matrices, which will be two-dimensional arrays, then the algorithm, like this, will tell you how to do multiplication just by variables, right? But that's not really helpful, so we're going to also do, a sort of visual way to do matrix multiplication that matches it. But the notation will end up looking like that when we write it down on the board, so that's why I'm drawing attention to it. So a matrix is square in the obvious sense if the size is n by n, so number of rows equals number of columns. Right, makes sense. If you draw that, it's going to look like a square. So we also have something called a diagonal matrix. These are the diagonal entries, but a diagonal matrix is something that actually crops up a lot if you're doing certain algorithms. So it is a matrix whose only entries are diagonal entries, or non-zero entries. Only non-zero entries are diagonal. So these are relatively easy to construct, right? We've got some 3 by 3 matrix, so I just write zeros everywhere that aren't on the diagonal. And I put whatever numbers I want there, right? And that would be a diagonal 3 by 3 matrix. So 1, 5, and actually 0 works just fine too. Doesn't have to be, doesn't necessarily have to be non-zero, but you know, it's just the stuff along with that. There is a specific matrix that looks like that we care about. So that's the identity matrix. So we call it the identity matrix because for a lot of operations, it behaves like 1. So the notation we use is IN, where n is the size. It's always square. And it's kind of the simplest looking thing you could imagine. Actually, I'm going to make it 4 by 4. Right? It's just, you've got this sort of the diagonal there. They're all 1s, everything else is 0. Right? So this would be the identity matrix I4, right? It's just the size 4, 1. Oftentimes, we don't even write down the size when it's pretty clear what we're talking about, right? Because our end goal is this behaves like 1. So we would just write I because it's the matrix equivalent of 1. Okay, so these are just some useful matrices. Let's now start talking about the things that we can do to them. Well, when we talked about vectors, there was something we needed to be able to do before we could really do anything with matrices or vectors, and that was, when are they equal, right? When are they the same thing? In this case, it's also the obvious thing, right? 2 matrices are equal if you compare them, entry by entry, and they're the same. You should just go along and check them. The matrices are equal if all their entries are the same. And importantly, they're the same size. Right? Because if this is is this matrix equal to that? No, they're not even the same size. It doesn't even matter, right? Okay, sure, we go along, we compare the first 3 things, and they're the same, and then 0 equals, there isn't even a spot to compare it to here, right? So it doesn't make sense. And that's going to be pretty common with matrices, is that there are size constraints that we often have to worry about, right? And this is actually something that students screw up pretty often. They'll just ignore those size constraints and just say, well, I decided it's this. And I'm like, okay, but you made that decision. I could decide a different one and get a different answer. So that means it's arbitrary, which means it doesn't make sense, right? If you can choose something and get a different answer, depending on what you chose, then it doesn't really make sense. So this is a pretty standard definition for equality. So just as an example, we've got these 2 matrices, and we're going to say they're equal. All it's saying is that, okay, this entry has to be the same as this. Good. Whatever x is has to be the same as that. So x is -1. These are the same. Y has to be that. Means x has to equal -1 and y has to equal 0. So equality, not that unusual. So addition, also not that unusual. It's exactly what you would hope it would be. Just like with vectors, when we said, okay, let's add them up, let's just do them, component-wise, term by term, just slap them together. Matrices, same thing, right? You just go along the entries and add them up. So that's already pretty nice. addition, we do this entry-wise. So as an example, I guess it doesn't matter. I'm just going to write down random numbers. 4, well, this is random, but let's add 0, -1, 2, 1, 5, -2, 3, 1, 2. It doesn't matter. We just add them up exactly how you would hope you would. So this first entry is this plus this. 1 plus 0, 2 plus -1, or you could say 2 minus 1, 3 plus 2, 4 plus 1, 5 plus 5, and so on. So 6 minus 2, 7 plus 3, 8 plus 1, and 9 plus 2. Right? It's exactly how you would expect it to be. 5, 5, 10, 4, 10, 9, 11. Nothing too wild there. Okay. This is another one of those examples I was talking about. We do have a size restriction here, right? These matrices have to be the same size. Matrices must be the same size. And again, this kind of makes sense because if you try to do this plus this, how do you possibly add them? Students will say, well, that gets added to the top left one. Why? Right? Why not? Why doesn't it get added to this one and then, you make this the block, right? Arbitrary. Why don't you do this added to this row and this added to this row and leave that one alone? Right? It doesn't make sense, right? You can't add these up because you have that choice and it's arbitrary, right? So no, it's not obvious that it would go top left like that because you could do any of them. Yeah.
Now, matrix multiplication must be really simple here.
No. We'll get there. But there is something that we can do that is also really simple. And most of this comes from the fact that vectors are just special cases of matrices. So we can do a lot of the same stuff. So another one is scalar multiplication. So this is exactly like it was for vectors, right? Works similarly to vectors. Just multiply all entries by that scalar. So if you had, say, 5 times the matrix 1, 2, 3, 4, that's just 5 times 1, 5 times 2, 5 times 3, and 5 times 4, right? Exactly how you would hope it would. That's 5, 10, 15, 20. Okay, so far, so good. Subtraction, I mean, do I really need to say it? Right? It's exactly the same as it works for vectors, right? How you would hope it would be. So subtraction, just going to say, works how you hope or you expect. No tricks. So we have this identity matrix. There is one more matrix that we would care about. I'm just sort of following the same structure that we had for vectors, right? There's also something called the zero matrix, which in terms of addition and subtraction behaves like 0. So it behaves like the number 0 for addition. and subtraction, of course. It's a bit unfortunate. What symbol do we use for the zero matrix? 0. Like, you can specify the size if you want, but there's not. You don't really need to, right? But it is exactly what you would expect. It's just zeros everywhere, right? No surprise. Just write down zeros in every single spot, and there's your zero matrix. Technically, it actually could be any size. It doesn't have to be square, but I mean, again, we often don't even write that, right? We just say 0. Okay, but there are a couple of other things we can do to matrices that are interesting. One of them is called the transpose. It's actually not a very complicated operation, thankfully, but it is technically a new one. So just like with vectors, we ended up saying, okay, well, we can do the dot product, and that's sort of a different thing, right? It's a new operation. So this similarly is a new operation. But good news, it's a simple operation. So the transpose of a matrix A, which we denote a T. This is not technically an exponent, it's just a symbol. It's saying, hey, this is the thing we're doing. It's unlikely that you would get that mixed up, but is the matrix formed from A by swapping rows with columns and columns with rows. Swapping rows with columns and columns with rows. So yeah, that's relatively straightforward. The way I handle it, so let's say we have a matrix that looks like this. -1, 2, 0, 5, 2. So we want to transpose this thing, right? So we're going to say T. What I do is, pick either rows or columns. So let's just say we take rows, take the first row, write it as the first column instead. Right, so this is 1 minus 1, so now I write it as a column. 1 minus 1. 2, 0, 5, 2. Right, so this essentially has the effect of like flipping it, right? It just kind of flips it around. It technically mirrors it along sort of an axis there, especially easy to see on a square matrix. But on a non-square matrix, it's a little funky. So that's why it's just, you swap the rows become columns, columns become rows. So it's easiest to just write them down like that. And the reason why we care about this operation is some very useful matrices are what are called symmetric. So that means if you perform this operation, it stays the same, right? Symmetric, like if you actually think about it, symmetric would mean, you swap the stuff, it doesn't change it, right? So that's what symmetric means. And there's a lot of useful algorithms and results that come on symmetric matrices. But my point here is this is just another thing we can do to matrices that ends up being relatively simple, right? It's just you swap rows and columns. So now, let's talk about the elephant in the room. Let's talk about matrix multiplication. So when we're talking about an operation like multiplication, it ends up being what I would say from a mathematical perspective, a little more complicated than addition. And it kind of makes sense if we think about just numbers. What is multiplication? It's repeated addition, right? What is 5 times 2? It's 2 added up 5 times. So that ends up giving us a lot of properties that are related to addition, but more convoluted and powerful. But if we just did that with matrices, if we just said, okay, it's repeated addition, we just get scalar multiplication, right? Because if you take a matrix and add it up a bunch of times, that's just let's say you add the same matrix up 5 times, that's 5 times the matrix. That is not a matrix times a matrix, that's a number times a matrix. So that tells us, okay, we need something a bit different. So first, I'm going to write down the formula. Because, again, it's useful for algorithms, so if you're coding it or something, then you're just going to have a bunch of for loops. I think, generally speaking, it's 3 of them. One to go over the rows, then one to go over the columns, and then you need one to create the addition that we're about to write down. But because of the way it works, I think the time complexity is actually O of n squared. It's not O of n cubed. Don't worry about that. Point is, it ends up being, there is a formula. It's gross looking. We're going to avoid the formula unless a computer is doing it, because there's a sort of nice way to do it. So if A is an m by r, so I am being very careful here with the sizes, and B is an r by n matrix, then the product which we normally just say AB, right? It's multiplication, is the matrix C whose ijth entry, so that's just, pick one of these little specific spots, is, all right, so it's the entry ij. So we need to do a bunch of multiplication and addition. It actually ends up corresponding to dot products. So we'll explain it in that way, which can be very helpful. But it's AI1 times B, is it 1J? Yeah. Plus AI2 B1 or B2J plus AI3 B3J, and so on and so forth, right? You just sort of go over this until you run out of numbers. So you should get it should be N, AIR, BRJ. Looks pretty gross, right? But you can see what I mean where a computer would be able to do this pretty well, right? Because, for us, keeping track of all these indices is pretty gross. But like a computer doesn't care, right? It's going to say, oh, you need this thing, I do this, right? And you can see where the loops would come in, right? You need a loop to go over I, a loop to go over J, but then you have 1, 2, 3 up to R, which is another loop, right? So it takes 3 loops to do this generally. Now, again, we'll talk about how to do this without the formula, but there is something important to note here. There is also a size requirement for multiplication. And it specifically has to do with, you see how we have this R? That's what's called the inner size of the product. They need to agree. And it kind of makes sense. If we define this multiplication like this, we go, this number is 1 and 1, 2 and 2, 3 and 3. And we keep doing it till we get to R. So if this were a 5 by 3 matrix, and this were a 2 by 5 matrix, then we're going to run out of numbers, right, in this formula. So those have to be the same. So the inner sizes must agree. So what I mean by that is you have this A times B. This is an M by R matrix. This is an R by N matrix. These two sizes here, they have to be the same thing. Otherwise, you can't do the multiplication. And when we do the finger motions, it'll make sense there too. You'd keep going and you'd be like, wait, I ran out of numbers. But fortunately, this produces a matrix, C, which we call the product. And we also know the size of this, M by N. So the size of the result is also written down in there. So, okay, again, this formula is a lot. Let's just do an example. And it actually sort of helps make sense of what's going on. I'll do sort of two approaches here. I'm going to actually kind of use this formula, but then I'm also going to use my fingers to show what's going on. So we're going to multiply the following matrices, 2, 3, 4, 5, times 6, 8, 3, 9, 10, 4. Now, if you're doing multiplication, especially in programming, there is something you should check first. Otherwise, your array would say, hey, index out of range. Let's write down these sizes. This is 2 by 2. This B has 2 rows and 3 columns. So we first should make sure these agree, and they do. So we're good, right? That also tells us we know we're going to get a 2 by 3 matrix at the end, right? The outer sizes become the new size. All right, so let's take a look at what the hell this formula is actually saying. So let's say we wanted the top left entry. That's C11. So that says every I we have here becomes a 1, and every J becomes a 1. So this would be A11 times B11, and these are numbers, right? Because these are just the things in the matrix. Plus, now we move to this one, A12, B21. And now we would keep going, but this formula tells us, hey, once you get to R, in this case 2, you don't keep going, right? So we just did, we hit 2. So let's actually plug in these numbers. So A11 is 2 times 6 plus this times this. So what actually is happening here is there's a sort of finger motion you can do here to do multiplication. This is the row we're doing in this left matrix. This is the column we're doing, like that. Right? You just move along the entries like that. So if we wanted the next one, so let's just actually write this down. This is 12 plus, oh, so why did I make the number so big? 27, 39. So let me show you what I mean with the second one. Let's say we wanted C12. So that's row 1, column 2, right? So this is row 1, column 2. Give me that number right there. So let's use this formula. So I is 1, B 1 times whatever the second number is, which is 2, A1, 2 times B2, 2. So A11 is this thing, B12 is this thing. And then A12 is this thing, B22 is this thing. So like that, right? So this would be 2 times 8 plus 3 times 10, which is 46. Why did I do this? So that finger motion is actually how you do matrix multiplication as a human being, right? This sort of formula thing, I'm just writing this down to say, hey, this is the formula we defined. The finger thing we're about to talk about matches this. So now let's actually just explicitly do that. So this entry here corresponds to row 1, column 3. So that means we're going to take row 1 in our left thing and column 3 in our right one, and then we just do this, right? We go through it. So 2 times 3 plus 3 times 4. So that is 6 plus 12, 18. And if you want, you could check that formula definition there and you'll get 18. And then we just rinse and repeat. So matrix multiplication is one of those things that initially it is kind of a lot, but once you do it enough times, you just go, okay, and you're doing the finger thing, right? I call it the finger thing. I don't know what it's actually called. Good enough. So this number here is row 2, column 1. Row 2 in the left, column 1 in the right. 4 times 6 plus 5 times 9. Oh man. 6, 12, 18, 24 plus 45 is 69, I guess. And then we just keep going, right? So I'm going to look up the numbers this time. So God, next one's 82. What is wrong with me? So this number here, row 2, column 2. Row 2 in the left, column 2 in the right, 4 times 8 plus 5 times 10, which is apparently 82. And this last one, like this, 4 times 3 plus 5 times 2, which is 32. Right? So there's just this process, this pattern to go through. And with that sort of motion there, that movement I'm doing, it makes sense that if these two sizes don't agree, it won't work, right? So like if I, let me just write down a quick example here as a hypothetical. So the formula here doesn't make sense, but also that sort of movement doesn't make a whole lot of sense. So if I had something like this, 2 by 2, and a 3 by 3, use the same one I keep using, then I would say, okay, top left one, row 1, column 1. 2 times 2 plus 4 times 2 plus, hey, wait a minute, I ran out of numbers, right? So that's a sign that's like, well, now what? Again, the mistake students do is they say, oh, well, it's 0. Why is it 0? There's no 0 written down. Where did you get that, right? It's not there. There's nothing there. So 0 in mathematics is not actually the same thing as nothing. Nothing is the absence of anything. 0 is a number. It's a quantity, right? There's nothing. They mean different things. So be careful about this, right? This is not defined. You can't even do it. Which is important because not every situation you run into with matrix multiplication you could do. With numbers, you have 2 numbers and you multiply them together. You're like, whatever, I just plug them into my calculator. I can do it. That's not true with matrices. If I give you 2 matrices and say, find the product, a valid answer is no. I mean, technically, that's a valid answer to any question I give you. If I give you one, you're just like, no, Travis, I don't want it. And I'm like, okay, fine, whatever. But like a correct answer in this case could be like, no, I can't do it. It's not defined. It's not possible. So that already leads us to think that matrix multiplication is a little weird because when we think about numbers, that doesn't happen, right? You can multiply any 2 numbers together, right? Even weird ones. But now we're saying, hey, there are situations where matrices, you can't multiply them. So already that's kind of a pretty big restriction that we have to have these 2 inner numbers agree. So that removes a lot of possibilities, right? There's a lot of matrices we can't multiply together. So I also mentioned that you can think of this as dot product, right? And I don't worry about if that finger motion made sense to you, then what I'm about to write, don't worry about it. This is just I've had some students in the past say, as soon as you explained it that way, it made way more sense. So I'm just going to write it down. So say the rows of A are, row 1, row 2, row 3, and so on, up to row M. There will be M rows of them because it's M by R. And the columns of A, or columns of B, sorry, are, well, column 1, column 2, column N, I guess. There's N of them. Okay, so what that means is we've got this matrix A over here times B. So what does A look like this? Well, we're saying, hey, this is row 1, this is row 2, and we got a row 3, and we got M of them, right? These are not numbers, they're rows. Okay, so that's all the rows. And then over here, we're going to say, okay, this is column 1, column 2, and so on. And there's some number of columns. These are not numbers, they are columns. But we can transform that definition to basically be, well, we're going to do that finger thing, right? We're going to go along row 1 and column 1 like that. There's another way to say that. That's row 1 dot with column 1, dot product, right? And then we just keep going, right? So this is row 1 dot with column 2. Row 1 dot with column 3, and so on. This would be row 2 dot with column 1. Row 2 dot with column 2, and so on, right? You just keep doing that. So you can think of this matrix multiplication in terms of dot product. And the reason why I think some students will find that helpful is it gives you kind of like an explicit formula that isn't like super gross, right? The first one we wrote down has a lot of indices and a lot of stuff like that. It's just saying, hey, take the first row and do that dot product thing with the first column, write it down. And you can do that on the side. And then this one is do row 1 and column 2, and then row 1 and column 3, and then rinse and repeat, right? So this definition has been helpful to some people, so that's why I write it down. It might even actually be helpful depending on how you implement matrices in Python or whatever, that this might be useful too. This is useful interpretation of it. Okay, so I don't want to go too much more into this. I just wanted to introduce the concept so that we can save it for next week. But right now, great, the marker lid. So this is sort of like linear systems, which I hope after this quiz you'll be convinced of it. It seems like a lot. It's overwhelming to look at first, and then you actually go and do it a few times, and you're like, wow, okay, that wasn't that bad. That has been my experience with students in general. This ends up being the same, right? It's like, oh God, he's doing a bunch of stuff. And then you actually do it, and I'm like, just do the finger thing. Just do that. And then students do it, and they're like, oh yeah, okay, it's not so bad, right? You might not be able to do it in your head, which is why I was like doing this. I mean, these big numbers especially, I try not to give you stuff like that. I don't know why this example's like that. I should change it. But, you know, you can do it on the side too, right? Which is why this also helps, because it's just a formula. So, okay, I want to, before we do the quiz, I just wanted to do an example so that I can get us warmed up to that. Because again, it's related, but it's not quite the same. So I just want to make sure that, you know, you didn't just pack all this into your head and then now I'm like, okay, the quiz isn't on this though. I hope I'm good to erase this. You can scream at me if I'm not. And I would probably jump because I am easy to startle. Like genuinely, it's terrible. My roommate will like walk behind me when I'm in the kitchen and I'll be like, oh. Okay. So this is worded in a different way. So it's, is X a linear combination of the vectors v1, v2, v3, and v4. So this is going back a bit. We did talk about this concept of linear combination. That's also why I want to bring us back. Okay, so obviously I need to tell you what these vectors are. So X is this. -1, 2, 1. It's just some vectors. v1 is -2, 1, 1. v2 is 2, -1, -1. v3 is -1, 2, 1. And v4 is something else, -1, 3, 1. So we just have to remember what this is linear algebra in a nutshell. The processes are not particularly complicated once you're used to them, but there's a lot of terminology and you have to digest it. So this is saying, hey, is this a linear combination? So then you just have to flip through your notes and go, what the hell is a linear combination? Well, a linear combination just says, can you do this? A v1, I'm even using nice letters for it, v3 plus d v4. So can we find A, B, C, and D so that this happens? I just want to find these numbers. So, okay, what does this look like? Well, we know what these vectors are. We don't know what these numbers are, but we know what the vectors are. -2, 1, 1, plus B, 2, -1, -1, plus C, -1, 2, 1, plus D, minus 1, 3, 1. Like that. Okay, but then we can just kind of do vector stuff, right? We just add it all together. And what do we get? Minus 1, 2, 1. Minus 2a plus 2b minus c minus d is that first one. We're just collecting all the terms together. A minus b plus 2c plus 3d. A minus b plus c plus d. Hey, wait a minute. This is a system of equations, right? Equation 1, minus 1 equals that first thing. 2 equals that second thing. 1 equals that third thing. So it's minus 1 equals minus 2a plus 2b minus c minus d. 2 equals a minus b plus 2c plus 3d. And 1 equals a minus b plus c plus d. So that is a system of equations, which we just spent an entire class talking how to solve, and we get to use the same techniques here, right? So, step 1, we state this thing. That's terrible. So we're finding this matrix, which we just read off from this, right? So it's swapped. This is the thing on the other side of equal sign. So that's going to be over here. This first part, this a part, is the coefficients, right? So this is going to be minus 2, 2, minus 1, minus 1. And then the stuff on the other side of the equal sign. So 1, minus 1, 2, 3, and then 2. And then we got 1, minus 1, 1, 1, and 1. That's our matrix. Now, there is actually a shortcut here. This is just me explaining how we do this. If we take a look at our vectors here, vector 1, 2, 3, and 4. Vector 1, 2, 3, and 4 are the columns of this matrix. X is that, right? So you could skip all this and just plug them in if you want, right? And that's fine. But this is what this represents, right? So we're trying to find A, B, C, and D so that this is true. And actually, it being a linear combination, we don't actually care what the numbers are. We just want to know, can we find them, right? There's two situations. Either we can't or we can. Yeah. It might be. Minus 2, 2, minus 1, minus 1, minus 1. So minus 2, 2, minus 1, minus 1. Minus 2, 2, minus 1, minus 1. And then the component of x is minus 1. I mean, fair enough. Look, it's so easy to... I'm just as likely to have made the mistake. So good to check. But now we just go through our process, right? We go through our row reduction here. So pick one, doesn't matter. I'm going to put row 3 as the top. We just go through our motions, right? 1, minus 1, 1, 1, 1, 1, minus 1, 2, 3, 2. And then we swap these two rows. And now we have a 1 at the top left. We use it to get rid of our stuff below. So row 2 minus row 1 and row 3 plus 2 row 1. So 1 minus 1, 1, 1. We don't touch that row. We know this is a 0. We designed it to be that. And so now we just have to figure stuff out. So we're subtracting this row from this. And remember, we're doing the whole row. It's not we're subtracting 1 from the row. No, we're subtracting this row, the top one, from the stuff that's here. So we're subtracting minus 1 from minus 1, so that ends up being a 0. We are subtracting 1 from 2, so that's a 1. We are subtracting 1 from 3, that's a 2. We are subtracting 1 from 2, that's a 1. We are adding 2 times this to this, so that's minus 2 added to 2, that's also a 0. Nice. 2 times this, so that's 2 added to minus 1 is 1. 2 times this added to this gives us 1. And then 2 times this added to this also gives us 1. All right, we're almost home free. So now we're going to subtract this from this, so we don't have to do any swapping here. Row 3 minus row 2. 1, 1, 2, 1. That's a 0. This minus this is minus 1. This minus this is 0. Okay, so we have that staircase shape, which is what we want. Now, my point here with linear combinations is we could keep going, right? That's totally fine. If that makes you comfortable, keep going. But we don't have to, because is it a linear combination is, can we find these numbers, right? Well, at this point, all we're going to do is we're going to move this up there and then this up there, and then we're going to write down the equations and solve it, right? But if we take a look at this, is it possible for us to do anything more to this that will cause us to have no solutions at all? Which, remember, would look something like this. So we got a bunch of zeros, and then something that's not 0 on the far right side there. Could that possibly happen no matter what we continue doing? It can't, right? Because what we would have to do is somehow this number is going to have to disappear, right? This 1 is going to have to become a 0. And then this would have to become non-zero, which all we're going to do is we're going to add this row to things above now in the process. So if we do that, then sure, these numbers will change, but this will stay a 1 or a minus 1, right? So we will never get something that looks like this. So the point is, this is enough to answer this question as written. If it said, find A, B, C, and D, then we would have to keep going, but it just said, hey, is it? And we could just say, well, yeah, it is. We can solve this. So yes, since we can continue to solve this. And so this is me just saying, hey, you could save yourself a bit of work if you do this. There is nothing wrong with continuing through the process if you're just comfortable with that and just keep going. And then you'll see that this won't happen. You will get some numbers for this. You'll actually have a free parameter here. So you have to choose a number or whatever, which ultimately means that there's actually infinitely many choices for A, B, C, and D that will make this true. So you just pick one, right? And then there you go. There's your A, B, C, and D. But I just wanted to remind you that the row reduction process is, try to create a 1 at the top left, use it to get zeros below it, cover it up, repeat, right? And then now what we would do if we wanted to keep going is we would turn this into a 1, and then we would subtract it from the stuff above, make zeros there, and then we'll go here and say, do the same thing there, and then we would be done, right? So, okay, big shocker what the quiz is. It's do some row reduction, solve some equations, but it's basically just doing this sort of stuff. So I will pass out the lovely gift of,